Okay. Hello, everybody, and welcome to the 7th session of the 14-part Microsoft SQL Server 2014 launch webinar series. So we're all very excited about the release of the new version of SQL Server. By the way, today the RTM bits are supposed to go live on MSDN, so be sure if you have MSDN, go check it out, download the latest release, and start enjoying this fascinating new product. And we're very, very honored to have today some of the people that actually were behind the design of some of the features that you're going to see with SQL Server 2014. Over the next few weeks, past virtual chapters will be hosting various speakers from the engineering and technical marketing teams who will discuss new functionalities and enhancements in SQL Server 2014. Before we get started, I want to share some information about PASS and tell you a little bit more about the virtual chapter, the new in-memory virtual chapter. My name is Ami Levin, and with me today is Ken Spencer. We were both going to lead the in-memory virtual chapter, and we're looking forward to seeing you in our upcoming meetings. So just a few words about PASS. I'm sure all of you are highly familiar, but for those who are new, PASS is an independent, non-profit organization run by, run by and for the community. PASS membership now has more than 100,000 members worldwide, and we support data professionals with the Microsoft data platforms to connect, share, and learn through virtual chapters, offering free online training such as the one you're currently attending. It's an in-person event including PASS summits, business analytic conference, and regional events including SQL Saturdays, SQL rallies. Please go to sqlpass.org to find out more about how PASS can help you boost your career. As a valued member of the in-memory virtual chapter, we're extending a $150 discount to the PASS Business Analytic Conference, which will take place in May in San Jose in California. So if you haven't registered yet, go to register online and use the discount code BAVC, that's all in capital, 25 when you register to receive your $150 discount. The conference will offer more than 70 sessions by the world's top business intelligence and business analytics experts and over 20 hours of networking opportunities with 1,000 data professionals from around the world. So expect to walk away with real-world insights for companies such as Microsoft, Wells Fargo, SurveyMonkey, Yahoo, Intuit, just to name a few, and best practices, prescriptive guidance, and strategic vision. I highly recommend you to find out more today at passbaconference.com, and remember the discount code BAVC25 to receive your $150 discount voucher. As you realize, this is our first meeting of the in-memory virtual chapter, and hopefully in the next few years you're going to join us for more sessions on anything that's related to in-memory technologies. So things like obviously in-memory OLTP in SQL Server 2014, and many additional features to come in new products, but also familiar things like in-memory column store indexes, a lot of BI in-memory features. So if you're interested in seeing, what's coming in the future of data processing in general, I hope you will join us for our future meetings as well. Be aware that all meetings are recorded and will be archived for future viewing on our website. And now I'd like to introduce Jos de Bruijn, who is going to talk about SQL Server 2014 in-memory OLTP. Thank you, Jos, and you're good to go.
Thanks, Ami. Just a quick check. Can you see my deck that I'm sharing? Because the tool shows still previous slides.
I'm still seeing the SQL Server 2014 webinar series opening slide. So maybe
that's what I see too. Okay, let me try something here in the tool. So in the meantime, hello everyone. My name is Jos de Bruin. I'm a program manager in the SQL Server organization. I've been working on the in-memory OLTP feature for the last couple of years. And I think you have already had a couple of webinars looking at introduction of the technology and also looking at things of interest for developers. What I want to do today is do a deep dive into the aspects that are especially relevant from the DBA perspective, especially around how to manage memory and how to manage the new data files that you have on disk. Now let's see if my screen is going to show. But either way, the key points I want you to take away from today's presentation is that the new memory optimized tables that we introduced with this feature, they have completely new data structures. So we don't have anything like old pages or B trees. No, they have new data structures that are optimized for in-memory. And also, you always need to keep in mind that your tables and your indexes, they need to fit in memory. And the second is that we have a new mechanism for durability of these new memory optimized tables. We have a new type of data files, new type of on-disk structure. This requires additional considerations when you are thinking about storage and about database recovery. So let's see. So we still don't.
Yes, I'm still seeing the So maybe what you should try and do is stop presenting and start presenting again. Sometimes it just resets and it might help.
Yes, I just did that. Okay. So let me just continue with the presentation. Hopefully you can look later at the slides, which I assume will be made available. So I want to give a quick recap of the feature. In-memory OLTP is a new feature in SQL Server 2014, and is specifically a performance feature for OLTP workloads. So if you right now are bottlenecked on, for example, latch contention or locking in the system, or you're bottlenecked on CPU with your OLTP workload, this feature can help you. Now, when we are thinking about the feature, we always think about 4 different pillars. The first pillar is the new memory optimized table and index structures. So the way we organize tables in memory optimized tables is completely different from traditional clustered or non-clustered indexes. The rows are not part of an index. The rows just live in memory and they are memory addressable. They're also not part of a page or anything like that. So we just use an 8-byte pointer to address any row in the table. And we also have new types of indexes that are especially designed to be in memory and to use the memory addressability of the rows. So for example, the indexes themselves don't contain any rows, they just contain pointers to the rows. And we also have a new type of index, which is the hash index, which I will mention a little bit later. Second pillar is that we want to deal with systems that have very high level of concurrency. So you can imagine you have a very high throughput system on a server with many cores, and you don't want this concurrent transaction to wait for each other. So typically you could get latch or lock waits in these kind of concurrency situations, but we designed our the system, the in-memory OLTP feature, the tables, the new storage engine to be completely latch and lock-free.
Okay. Jos, just
Yeah.
1 second, please. So
Yeah.
what I did, I took over. I'm now presenting your slides.
Okay.
So please, and I think that the people, I get responses that people can now see it. So I think we should continue this way. Can you please tell me what slide you want me to be on?
Is it the in-memory OLTP recap? That's the one.
That's slide number?
I do not know the number of the slide. The title is in-memory OLTP recap.
Okay. Let me look at that for a second. In-memory recap. Okay, I'm here. So just say next slide, and I'll do the transferring of slides for you. Okay?
Yeah. Okay. Great.
Okay.
So the third pillar we have is native compilation of your business logic and stored procedures. So to better utilize the CPU to be able to do more with your existing CPU cycles, we take the query plans for T-SQL stored procedures and we compile them to native code, to DLLs, for very efficient execution. And finally, the feature is fully integrated into SQL Server. So you use a familiar T-SQL language, use familiar management and development tools. Things like backup restore and always-on availability groups are fully integrated. And also, I think one very important aspect here is that you can have both memory optimized and traditional disk-based tables in the same database. So the size of the total size of the database is not limited by the size of the memory. Your hot memory optimized tables need to fit in memory, but the rest of the database can remain on disk. Okay, next slide. So when you're thinking about what are the main concerns for database administrators when thinking about in-memory OLTP, there are two main aspects we think about. First is memory usage and management, and the second is on-disk storage for durability. So, memory usage, that is kind of obvious. You have your tables in memory and you need to be able to manage that. And the second, on-disk storage, is the main thing here is that we use a new persistence mechanism using append-only data and delta files that you do need to think about when you're provisioning storage and think about the hardware characteristics for the drives where you put those files. Let's go to the next slide. So let's first talk about memory usage and management. So I'm now going to the slide in memory data structures, and there is some animation in there, so it may be easiest just to fill out the slide. So when thinking about the new in-memory data structures, there are two main components. First, there's the table rows, right, where we have a new format for rows, and the structure of the rows is optimized for memory residency and access. So one key thing to keep in mind is that the row is our atomic data storage unit. So we don't have any pages or anything, we just have rows that live in memory that are addressable, and they have a new format which I will discuss. And second, each row has only one copy. So indexes don't have copies of the row or copies of part of the row. No, indexes live besides the row storage, and they in fact point to the individual rows. There's no duplication. Also, one consequence of this is that every index is covering. So we don't have a notion of included columns because all columns are virtually included. Then when you think about indexes, we have two types of indexes. The first index is a hash index, which is especially optimized for point lookups. And in fact, it does not support range scans or ordered scans, which you may be familiar with when using traditional B trees. So Also, when you use hash indexes, you need to be very deliberate and need to be sure, hey, I really want to optimize point lookups and I don't need to do range or ordered scans, so I can use a hash index. And then you have, for the range and the ordered scans, we have the non-clustered index. So you can scan a range or scan the rows in order. And this non-clustered index behaves, from the behavior point of view, pretty similar to a traditional non-clustered index on a disk-based table. However, the implementation is very different. We have a structure called the BW tree, which is kind of a variation of a B tree, which is optimized for in-memory and for high concurrency. So it is a latch-free structure, and the pages in the BW tree don't have a fixed size. They have a variable size. They're always packed. Plus, also, I think I forgot to mention this on the slide, all these indexes are maintenance-free. So a hash index is a static structure, so there's nothing to be maintained about it. And the non-clustered indexes, BW trees specifically, they are self-maintaining. So as a user, you don't need to do any defrag or rebuild or anything like that. And finally, an important point here is that these indexes do not exist on disk. They exist only in memory. This is one of the ways we optimize for in-memory. So these indexes are in fact recreated during database recovery when you restart your server. And if you're thinking about an always-on availability group scenario, the indexes as well as the table rows there are always in memory on the secondaries, so that you can use them immediately when you fail over. Let's go to the next slide, row format. So this is roughly what a row looks like in a memory optimized table. We have a row header and then a payload. The in-memory OLTP storage engine doesn't know anything about the payload. That's more the language area. But the storage engine does know about the row header, the structure of it. So what you see here is we have a begin timestamp and end timestamp. So one of the mechanisms to avoid having to take any locks or latches is to use multi-versioning. So we have a multi-version system, and the tables, the multi-versioning is built into the table data structures. So every row has a begin timestamp and an end timestamp. The end timestamp indicates until when that row is valid. So when you have your query using snapshot isolation, you say, hey, what is my read timestamp? And you look at the begin timestamp and end timestamp of the rows to determine which one applies to you. We have a statement ID used for internal purposes, a link counter used for garbage collection purposes, and then we have the actual links to for the indexes, which you see on the right. Because each entry in an index can have multiple rows in it, and this is implemented using a linked list data structure where each row points to the next row in that same entry in the index. We'll have an example on the next page. Let's go to the next page. Actually, the example is in the following one. So this is the hash indexes slides. Let's just expand it. So a hash index, the way the index structure looks like, is just essentially a hash table. It is an array of index pointers, and we think of these as the buckets. So what you do in order to figure out in which bucket to look for your row is you hash the index key. This will tell you which entry you have in the hash table, and from there you go to your row. So each of these buckets will contain a pointer to the first row in that bucket. And we have a built-in hash function, which is pretty close to random, so it produces a pretty even distribution, usually, of rows over the hash table. But of course, you can always have collisions. So collision is where the hash function, the built-in hash function, maps two different values to the same bucket. And what happens in case of such a hash collision is we create a chain of different rows. So let's go to the next slide, memory optimized tables and hash indexes. So this is a view of a table that has two hash indexes. So in this case we have a hash index on name and a hash index on city. And in this particular example, the name Jane is hashed to the first bucket of the hash index on name. The name John is hashed to the third bucket, and the name Susan to the fourth bucket. So this is pretty straightforward, these pointers. And then also you see there's only one row in each of these buckets. But then when we look at hash index of city, so what we have in this case is the city Prague is hashed to the third bucket in the index. But we actually have two rows that correspond to city Prague. That means you will need to have two rows in that same bucket, and you can see there is this chain pointer from the first row, Jane Prague, to the second row, John Prague. And we see the last bucket, so Bogota is hashed to the last bucket in this index. So this should give you roughly an idea of what the structure of a hash index. Let's go to the next page, non-clustered index BW tree. So this is what a non-clustered index looks like. So this will probably look somewhat familiar to you, as it does look somewhat similar to a B tree. So you have different levels. You have your root level with a root page, and then each level of the index you have a number of pages. So in the middle you have these non-leaf pages. At the bottom you have the leaf pages. Now but the key differences are between this and a B tree is, first off, this data structure is completely latch and lock free. So you never take a latch on any page if you need to modify it. Instead, you create a new version of the page. So we use also a form of versioning in this data structure. Second is that the page size is variable. So we don't say, hey, this page is going to be 8K and it's going to be filled up to an X percentage. No, each page is variable size, and all pages are packed, completely packed. So there's no empty space in a page. And if you actually want to make a change to a page, you write a new version of the page. Well, actually, technically, we have delta pages, which show a delta between an old version and new version of a page. And then if there is enough change, we create a new version, completely new version of the page, integrating the delta page. And another key difference, finally, with B trees is that the leaf pages don't contain actual data rows. No, they contain pointers to the actual data rows. Now, one thing that you do need to keep in mind is that you do need to have the index key in these pages at the various levels. So this example has an integer index key. Where you see at the top you have these numbers like 10, 20, 28, etc. But you can imagine if you have like very wide index keys that also this data structure will become bigger. Okay, let's continue to the next one, memory usage and monitoring. So I want to talk about two aspects here, considerations and management. So first, you need to think about how much memory you actually need for your data and also to sustain the workload. So for table data, because we have this multi-versioning and you may have a running workload which creates new versions, they do get cleaned up but not immediately. So therefore, we generally recommend to see what the behavior is of your system under a stressed workload. But a good rule of thumb to start with is assume about twice the size of the data that you will need in terms of memory. For index data, the hash index is fixed size, so fixed on create, and the non-clustered index is going to be a variable size, and the size will depend on the number of rows as well as the index key size. In terms of management, we have two things. One is configuration. So you may want to make sure that that adding rows to memory optimized tables will not put pressure on other workloads in the system. If you would not put any cap on the size of those, you would just keep adding rows to the tables and push out all memory consumers in SQL, like for example push out the buffer pool, and this can lead to degradation in performance and stability in the system. Therefore, we do have a memory cap. In fact, we have a memory cap even if you don't use resource governor. So the default pool, you can usually not go beyond 80% of the pool size for your table data. But you can also create a dedicated resource pool using resource governor and define like how much memory you want to allow the memory optimized tables to use. And then for monitoring, we give you a whole bunch of tools, DMVs, SMO with SSMS, of course, and various reports in Management Studio as well. Let's go to the next slide on garbage collection. So garbage collection, I actually don't want to go into a lot of detail about this for time purposes, but just to give you a brief glimpse, garbage collection, what we do is we clean up old row versions that are no longer necessary, and for that we have a garbage collection process that runs continuously in the system, and there are two aspects here to keep in mind. Is we have like a dedicated thread which once in a while does some cleanup, and also active transactions in the system, they work cooperatively with the garbage collection thread to clean up stale rows. So if your index scanner encounters a stale row in an index, it may decide to do part of the garbage collection work. So I want to skip the next slide, which goes into a bit detail about garbage collection. Instead, I want to go to the slide on resource governor integration. So the goal here is to limit the maximum amount of memory that is used by in-memory OLTP to prevent performance degradation or instability of other workloads in the system. You can imagine if you also have disk-based tables in your database, you may need the buffer pool as well as create some query execution memory for that. And also if you have a multi-tenant scenario with multiple databases in the same system, you will want to limit the memory allocation for the individual tenants. So what you would do in this scenario is you create a dedicated resource pool for your database. You bind your database to the resource pool, and then you configure the maximum amount of memory that can be used by this pool. And then in addition, within the pool, there is a certain maximum percentage of memory that we use for table data, because we may need to use also some additional memory for some further processes like garbage collection, transaction management. But the user table data will have this max, and it will depend also how big the pool is. So if your pool is like only 8 gigabytes, you will get at most 70% of it. If you have like more something close to 100 gigabytes, you will get about 90% of it. And that is, we want to make sure that the system remains stable even if you have a bit less memory, and therefore we need to make sure we reserve enough memory for the system to remain stable. Okay, let's go to the next slide, which is actually a demo. So this might be a bit more problematic for the screen sharing setup, as I am not able to share my screen. So I think we'll need to skip over the demo for now. You can look at the script which is in the notes section of the deck, which I assume will be made available to you. Okay, then let's go to the next slide on disk storage for durability. So this is the second big concern that you have as a DBA. You want to manage the storage in the system. So let's go to the next slide on durability. So you can declare your memory optimized table as being durable or non-durable. And we use the syntax durability equals schema and data for the durable part, which means that both the schema of the table and the data in the table are durable and will survive server crash. We have the non-durable variant, which we call schema only, where only the schema is made durable, but the data is not. So if your server crashes or you do a failover to an always-on secondary, the data in your table will be lost. So therefore, also because we don't like data loss, the default, if you don't specify anything, is your table is going to be durable. So we have the full durability guarantees, like if your transaction commits and the server crashes immediately after, if the server comes back up, all the modifications by that transaction are persisted in the database and will be visible immediately after recovery of the database finishes. But non-durable tables are useful in certain scenarios, like especially if you have transient data, such as in ETL scenarios, or if you have something like user session state. Then, well, we have mechanism for this durability. So first off, what's not mentioned on this slide, but what is the case is that in-memory OLTP fully integrates with the database transaction log. So operations on durable memory optimized tables are written to the transaction log. And also we have another persistence mechanism using what we call checkpoint files in a new type of file group, memory optimized data file group. And one thing to keep in mind here is that the access pattern for this storage is different from your traditional data files like the MDF, NDF files. Well, what we did is we optimized our access pattern for streaming storage, because we know that often sequential I/O is typically faster than random I/O. So therefore we said, hey, let's make this sequential. So we have these append-only files, and during database recovery, also we read the data in order. So that brings some special considerations that we'll mention later on. And also, another thing to keep in mind is that a file group, this memory optimized data file group, can have multiple containers, so you can spread your data over multiple disks, which will happen especially with recovery, which often happens at the speed of I/O. So let's go to the next slide on logging. So memory optimized tables, they use the database transaction log to persist the log records. And we have a new type of log record which has a standard format of a record header, and then we have an in-memory OLTP specific piece of log content which is understood by the in-memory OLTP storage engine. Then also important to keep in mind is that all logging is logical. So we don't have any log records for any physical structure modifications, nothing for index operations, anything like that. So we only have row insert and row delete, in fact, because an update is, for us, it's just a delete followed by an insert. So we have only row inserts and deletes. And there are a couple of log records also generated by the storage management, the on-disk storage management, but that is independent of the rows, in fact. And then because we are actually always in memory, we don't really need to worry about accidentally data being written to disk before the log record is persisted. Therefore, we don't need any undo information. So also database recovery for memory optimized tables does not have an undo phase, it just has a redo phase. And in fact, what we do is we don't log every operation. We don't log every insert, update, delete operation. Instead, we log everything for the particular transaction. All the inserts and deletes done in a transaction, we log it at the end in a single log record. And finally, in terms of recovery models, we support all three recovery models, full, both logged, and simple. But one thing to keep in mind is that for now, at least, all operations on memory optimized tables are fully logged, including bulk inserts and such. Let's go to the next slide on disk storage. So because we have the streaming storage, we thought, hey, we can use some technology that already exists in SQL Server. So under the covers, we in fact use file stream technology for the storage. This will already give us some checksums. We do also some single bit correcting, error correcting on the files. And now what are our files, in fact? So we don't have one big data file for all of your memory optimized tables. No, what we have instead is we have a bunch of data files and a bunch of delta files. So the data files, which are about 128 megabytes in size, they store only the inserted rows. So these are append only. So whenever you insert a row, it is going to be appended, appended, appended over time. This will just grow, and whenever a 128 megabyte data file is full, we open a new file and start writing the rows there. Now what happens when you do deletes? We append this delete to a delta file. So we have the delta file will have references to deleted files, deleted rows in the data file. And then once in a while we merge these files to reclaim the space. So let's go to the next page, storage data and delta files. So here you see a view of what a data and delta file could look like. So we often talk about pairs of these files. So you have a checkpoint file pair, and they together they cover a certain transaction range. So in this example, they consider the transaction timestamp range 0 to 100, because timestamp is just incremented integer, right? So 0 to 100, and the data file has all the rows that have been inserted. So that is the timestamp of the transaction that inserted it, the ID of the row within the transaction, and the ID of the table that the row belongs to, and then also the row payload. So as you can see, actually the row format here is different from the row format in memory again. So whenever, except for the row payload, the row payload is always the same, but the row header is different. So whenever we run recovery, we recreate the rows in memory with new begin timestamps and everything, but with the same payload as you have in the data file. And then we have the delta file, which just has the references to the rows in the data file. So the transaction, the timestamp number, the insert timestamp, and the row ID together are a unique identifier for a row. And then we also record the delete timestamp in the delta file to figure out at what point it was actually deleted, in case we don't want to redo everything. In case we want to redo to a certain point in time, we can do a cutoff based on this delete timestamp. Okay, let's go to the next page. This page has a somewhat complicated animation. So as I don't have control, I will not run you through the whole animation, but let me just describe what happens here in chronological order from left to right. So what you see here at this bar at the top, what this represents is the database transaction log file. And then, well, not necessarily the file, but the log, right? In general, we have the log in memory in some buffer, and we flush this to disk, but very often it stays in memory. And usually, the offline checkpoint thread will read in memory from the transaction log. So we have this offline checkpoint thread for memory optimized tables, which what it does is it scans the log to find operations on memory optimized tables, and it takes that information and persists it to disk in the data and the delta files. So the first log record is delete with timestamp 110. So this will go in the first delta file, so on the left, because it has range 100 to 200, so it will get the delete with 150. Then there's a log record for disk-based tables, which will skip over that. Then there's a delete of a row with timestamp 450, so that is that will be added to the fourth delta file. And then there's a delete of a row with timestamp 250. This will be added to the delta file of the second file pair. And then finally there is an insert operation in, and this is into some memory optimized table, and this will always be inserted in the open data file. At any point in time there's one open data file, and this has an open range, and the new rows are inserted in there. At some point when this data file is full, it will be closed and a new file will be opened. Okay, let's go to the next page, merge operations. So the previous discussion should have given you kind of a view of what we do with how we populate the data and delta files. So we keep adding the inserted rows to the data files, and we keep adding references to deleted rows to the delta files. But then if you have your workload running and you don't do anything else, these files will just keep on growing and growing and growing, even though you delete a lot of data. So what we do to reclaim space and also to speed up recovery is we have a merge process going on. So a merge, what it does is it takes two pairs, two adjacent data and delta file pairs, and merges them into a new pair in the process, removing all the rows from the data files that were marked as deleted in the delta files. We do that because, of course, if you have deletes, a lot of rows will become stale, and typically if more than half of the rows are stale in a particular data file, we will want to reclaim that space, both to reduce storage and also to improve the recovery time, because during database recovery you need to scan through all the data files. Now a merge is a background operation, so it does not affect any ongoing workload. It does not block concurrent deletes in any of the affected file pairs, for example. We have then a notion also of checkpoint file garbage collection. So when you can imagine, like you merge some files right into a new file pair, but you still have the old files on disk, and we have a garbage collection process which then actually removes these files. Two things to keep in mind here is that this does rely on file stream garbage collection, and also it requires database checkpoints and log truncation to actually make progress. So if, for example, you have full recovery model, you don't do database backups, these files will not get removed from disk. And also, if your system is idle, there is no workload, meaning there are no checkpoints, and no database checkpoints are happening. That also means that the files will not get cleaned up. Oh, and one thing to point out, as I will not be able to do a demo, is that we do have this DMV, DMDB, XDP checkpoint files. This shows all the checkpoint files in all stages of garbage collection. And if you look at the demo scripts that you will see later on, there are a number of queries which will give you relevant information based on this DMV. Now, visual representation of what a merge looks like. This is again animated slides, so maybe a bit more difficult, but I can try to talk through this. So, what we have here on the left, as of let's say time 500, let's say the timestamp has advanced to 500, we have 4 file pairs. With the 2 pairs in the middle, the 2 to 300 and 3 to 400, they're both like half empty, meaning there's this red bar you see. This indicates how many rows are included in the delta files. So the second file pair, we have about 2/3 of the rows are stale. In the third file pair, about half the rows are stale, and you will want to remove this. So what the merge process does is it picks up these file pairs and decides to do a merge. So then the system first marks these old file pairs as under merge, and at which time it constructs a new file pair that has the new data and delta for these ranges, the new merge file pair. And you will see here also that it has a new transaction range of 200 to 400. You can also see here that the delta file is not completely empty. There are already some deleted rows in there, and these are the rows that were deleted while this merge was ongoing. So that is how we allow for concurrent deletes while merge is happening. And then in the end, the files were under merge, and then they get phased out of the system, and eventually they will be removed from disk. Okay, so let's go to the next slide, storage considerations. So similar to thinking about memory, you also need to think about like how you provision storage. And with memory, the main consideration is the size and how to configure and manage it. With storage, there are 2 considerations. First one is the capacity, so disk space available, and the second one is performance, because if you have slow disks, those can become a bottleneck, especially when you use in-memory OLTP, which can push the system harder, but still the transaction log will always remain a bottleneck unless you use something like non-durable tables or delayed durability. So let's first look at the data files. So what you need in terms of disk space available is, well, it is as usual, it is workload dependent because this highly dynamic system and in certain patterns can generate more size than others. Now, what we have seen is with a very high throughput, typical order processing workload, which we've been using for benchmarking, we did not see the size on disk go beyond the size on memory, even when running this at a high stress level for 24 hours. But I mean, this is one access pattern. If you have another pattern, you might have a different amount of disk space needed. So in general, as a rule of thumb, start with between 2 and 3 times the size of your tables in memory, reserve that for disk, and see how this works out. And in terms of performance, what type of device to use, the main consideration here is your RTO. So that means you want your recovery to run fast, and you have certain RTO requirements. So you need to provision the storage that has the sequential I/O bandwidth to meet your RTO, because you need to load all this data on disk during database recovery. In general, we recommend either to use something like SSD or some high-end spinning media. Spinning media is still fine as long as it's fast enough, because we mainly do sequential I/O. We don't do random I/O, so SSD is not necessarily a requirement. When thinking about log in terms of capacity, well, rule of thumb, what we often say is, well, yeah, assume the size is going to be similar to what you have for your disk-based tables before you do migrate to memory optimized. However, in general, we do use a bit less log because we don't log index operations. But it's still the size of data. In terms of performance, latency is very important. So using SSD or PCIe would be recommended here. If you have like a higher latency device, you can also consider using delayed durability, which is a feature which allows transaction commit without flushing the log record to disk. But there, you do need to consider that if you use this feature, you commit your transaction, the server goes down immediately, the changes from that transaction may be lost. But all the transactions will be made durable. So let's go to the next slide on backup. So backup for memory optimized tables fully integrated with SQL database backup. So the new file group is backed up as part of your database backup. If you do a full backup of your database, the file group is just going to be there. Also differential backup is also supported. So this means that your existing backup scripts should work often without any changes, or well, maybe minimal changes to account for placement of the file group on a database restore. That's something you do need to keep in mind. Finally, the transaction log, well, the log records for memory optimized tables are simply persisted in a database transaction log, so they are automatically included in transaction log backups. Let's go to the next slide on recovery. So what happens during database recovery, which is run either on restore or on server restart, is that first we have analysis phase where we find what is the last completed checkpoint. Then we load data from the checkpoint files, the data and delta files in memory, and reconstruct the tables and indexes. And we do parallel load. So each core loads in parallel, and well, the more I/O devices you spread your files over, the more gain you will get. Then there's a redo phase. So after the data from data files is loaded to memory up to the last completed checkpoint, we do redo to apply the tail of the log. So from the last checkpoint, this happens concurrent with redo on all your disk-based tables. And there's no undo phase because, well, only committed transactions are logged. So there's no need to worry about that. Let's go to the next slide. Parallel recovery for memory optimized tables. So this diagram sketches what happens when you load in parallel. So in fact, what we do first is we take all the delta files, we load them in memory and construct delta maps. And these maps are used to figure out which of the rows in the data files have been since deleted and should thus not be loaded in memory. And then we load the data files essentially through the map, filtering out the deleted rows, and then construct the tables based on those rows. And yeah, we do this in parallel within one container, but also across containers. So what you do need to keep in mind here is that the impact on your RTO. So especially the speed of your I/O device as well as the size of your tables. That is very important. If you have let's say 100 gigabytes worth of tables, and you have an I/O device that, let's say, that does 500 megabytes per second, then you need to keep in mind you will need 200 seconds to load all this in memory. Another thing to keep in mind, or that I specifically want to call out here, is the CPU cost of non-clustered indexes on big tables. So what we do essentially during this data load, we insert into the tables, and insert into hash index is extremely fast. Insert into PW tree indexes, that takes a little bit more time. So you may become CPU bound during recovery if you have non-clustered indexes on big tables. So would recommend to test this in your scenario to see if you can meet your RTO requirements. Let's go to the next page. This is again a demo. So this is the demo for logging and storage. You will find the script in the notes. It has some queries which show you aspects of the checkpoint files of the storage, and will also show you some aspects of the log. Specifically, one aspect is that for disk-based tables we log row inserts in every index. So if you have a table with 2 indexes, we log actually 2 row inserts, whereas with in-memory OLTP we log only 1 insert, no matter how many indexes you have, because our logging is logical. And the second is that we put everything, all the information about the inserts and deletes in a single transaction. We put that in a single log record. And there's also a script in the notes which will show you how to crack open that particular log record and see the memory optimized table operations in that log record. So let's go to the next slide. So basically, to reiterate, the key takeaways here is that the new tables and index, they have completely new data structures. So don't think about B trees and how you used to maintain them, and how you had pages for rows and pages had fragmentation. All these things don't apply. We have completely new data structures optimized for in-memory. Every row is always addressable by the same 8-byte pointer, 8-byte memory address. One consequence is that all the data of your tables and indexes does need to fit in memory. And you saw what you can do to configure your memory, so to make sure that that they don't push out other memory consumers or other tenants. And we have some memory monitoring tools, which there are some DMV queries in the demo script. And you can also look in Management Studio, if you right-click on a database and then under Reports, there's a report called Memory Usage by Memory Optimized Objects. And this will show you a nice pie chart of the memory utilization in your database. The second key aspect here was durability of memory optimized tables, especially as we use this new type of mechanism for persisting the changes in the new checkpoint files, data and delta files. There are new considerations on how much storage you need to provide, and considerations for the hardware there. And one thing specifically to think about is the time need for database recovery, as we do need to load all the data in memory during database startup, and database is not available until this recovery has finished. Let's go to the next slide. Here there are a number of resources where you can find a bit more information on in-memory OLTP in general, as well as the specific aspects we covered here about memory and storage. Go to the next slide. I guess we can now do some Q&A. If there are any questions.
few questions, but unfortunately our time is up. So what I suggest is that for all the people who had questions, you can please forward that to the virtual chapter's email address, which is imvc@sequelpass.org, and we'll send these questions for Jos. Another forum, you can ask your questions on the MSDN forums. I know Jos is also monitoring that, so you may, and other people from the staff, so you can get your questions there. So I want to thank you very much for attending today's demo. I hope you find it as fascinating as I did. I would like to thank Jos very much for your enlightening speak. And we're sorry for the technical challenges, but I think we've managed to do a pretty good job even with those technical challenges. So thank you very much. Remember, if you have any additional questions, please email those to imvc@sequelpass.org. And I hope to see you next month in our upcoming meeting regarding additional features of in-memory technologies and SQL Server. So thank you very much for attending this session, and hope to see you again next month.
Thanks, everybody. See you next month.
Thanks.